Greetings, everybody. Welcome to the first uh, ever virtual star party for Carlton State University. We are doing this the very first time, so we are looking forward to showing you some celestial objects, some planets, the moon, and also some deep sky objects. While we are showing the objects, you are welcome to pose your question on the chat group. And one of my students, Marian, is going to tell me when there is a question and I will try to address the question. The plan is to start you off with a brief introduction to the Tarleton telescope. You should be seeing a image of the telescope right now, and I'll try to point it out with my mouse here. This is a 0.8 meters, 32-inch remote control telescope. It can be used from anywhere around the world if you have the access code. The dome itself is also computerized, so when the telescope moves and points in the different directions, the dome will also move it. And I will show you just one example when we move the telescope. Right now, I have the lights on in the dome. I will have to turn off the lights so that we can look at the objects later on. Just to give you an introduction, this telescope sits on a concrete pier that goes about 10 feet deep into the ground, and there is an extension on the concrete which is about 15 feet, and that is to help counterbalance the weight of the telescope. This facility is completely vibration free. A slight vibration will show up in the image, and you will see the blurriness there. The mirror itself is enclosed in this cage over here, okay? And there is a CCD camera that is connected over here to the computers. This CCD camera is very sensitive to light. It is designed for deep sky objects. So I'm going to show you some solar system objects, but it will be through another telescope which is outside the observatory. It's a smaller scope, and it can show planets and moons much better than our CCD camera is captured. Plus, this CCD camera is a grayscale camera, so it's not going to show color. It will, show you a lot of details in deep sky objects, which will otherwise not be visible in a small telescope. On this telescope, there is a small refractor telescope, which is a Takahashi 6-inch, and we have a video camera on it too. But because we are using a telescope outside, we will not be using this Takahashi telescope. As I mentioned, this whole facility is computerized, remote controlled. I use it from my home every night, or not every night, but at least many nights a week to collect data, scientific data. And I have several students who work with me on scientific projects obtained from this telescope. Unfortunately, it's already dark outside, so you cannot see the outside view of the building. But during that, if you saw that, you will see the observatory. There's also another camera mounted on top of the telescope, and that will show you what you're looking through the telescope if you wanted to use the video cameras. We are not going to use these video cameras for tonight. This is mostly to show you what the telescope looks like, and these are available to the observer at night to see if there is something that they need to check out in terms of where the telescope is pointing, or something unusual in it. I am going to swap screens in a few minutes over here with another screen, and I am going to show you how, first, before we do that, I'm going to show you how the telescope moves. Okay, so I'm going to go ahead and move the telescope to one of the deep sky objects, and you will probably see the telescope move and the dome rotate. So concentrate on this screen over here, the one on the top right hand side. All right. All right. Hopefully. I hope you saw that motion. It's not a lot of motion because the object that I'm pointing at is actually very close to the current position of the telescope. So I'm going to go ahead and turn off the lights. All right. You will see me stop my screen share just for a few minutes, so don't go anywhere. I'm going to swap screens here. So you should be seeing a bright star in there right now, but that is because I haven't taken a snapshot of a deep sky object. So I'm going to, take a snapshot of a deep sky object that I'm pointing, and I'll say a few things about this of the object that we are looking at. You can see here on the screen that the camera is exposing for about 10 seconds. And you can see that, I need a little bit more exposure time. So I'm just going to go ahead and increase that to 60 seconds. All right, so this object is called the Ring Nebula, is in the constellation of Lyra. Its Messier catalog designation is M57. And you will see it come up here in about, 30, 40 seconds. There you go. You can see this is a planetary nebula. And if you look very closely, there is a white dwarf star right here in the center. And I can move my cursor around and you can see the star in the center there. Okay, so this object is about 2,600 light years from us. It was discovered by Charles Messier in 1779. And the size of this object is about 1.3 light years. 1 light year is about 6 trillion miles. Okay, and this object diameter is about 1.3 light years. Astronomers have calculated that it's about 7,000 years old. Its mass is about 0.6 times the mass of the solar system. And although you see like a flat ring, but actually this is a two-dimensional image. So three-dimensionally, this is a prolate spheroid. Okay. Now, as I told you in my introduction, our camera is designed for deep sky objects. So you can see a lot of stars there. And I can probably spend some time, try to focus the stars too. They're not, it looks like there might be a little bit of focusing required but I want to show so many deep sky objects tonight. So I'm not going to spend a whole lot of time trying to focus it. So you can see that, in this planetary nebula is basically a dead star. So astronomers think that our sun is going to become a planetary nebula, and which will not look like this. It will have a different shape. But basically, when a star dies and all the nuclear fuels are exhausted, gravity begins to collapse the core, and the shell, the envelope of gas, which is loosely attached around the star, begins to expand. And so what we are seeing is a ring of gas that is expanding slowly. And in millions of years, it will thin out and disappear completely. So this is, there are a lot of other stars around it too. So this is one of the objects that I'm looking at right now. If you have any questions, please do, go ahead and post it on the chat. And I'm now going to go ahead and take you to a small telescope where we are now looking at the crescent moon, as you can see. Laren, stay on the moon for a while.
One question.
Yeah, go ahead.
And this is from Brasida Giannis, and they are asking, what are some of your research projects about?
Okay, so all right, so the question is, what research projects we do at Carlton. We have two astronomers in the physics department. Myself, my interest is in binary stars, eclipsing binary stars, exoplanets, and I also do data mining, also. And then my colleague, Dr. Michael Hibbs, he does research in near Earth asteroids. So, and he also studies supernovas as well. So between the two of us, we use the telescope to collect the data, and we involve a lot of undergraduate students in our research projects. All right, so what you're looking at on the screen, right, okay. So you should be looking at the moon. So I have a student outside who is managing the small Dobsonian. You can see the moon, you can see the craters, and this is called the Terminator, the part where you have the device, the dark side with the bright side of the moon. You can see many, many craters there. In fact, in another few days, the moon will be so bright that we will not be able to do a lot of deep sky objects. So that's why we chose this particular night, because it's going to be pretty nice and dark. And it so happens that we also don't have clouds in the sky. So it's particularly good for deep sky objects. All right, so I am going to, choose another deep sky object in a few minutes over here. And I will bring up the view for the telescope, swap windows here. All right, I'm going to turn on the lights. Then I'm going to go ahead and select another object. So it'll take me a little bit of time, maybe a couple of minutes, and I'll stay online. Is there any question in the meantime?
Miles wants to know if we are going to look at the Andromeda Galaxy.
Yes, I do have that on my list, and we'll give it a shot in a few minutes here. So you should be looking at the telescope moving, and the dome also will move so that it is aligned with the telescope. And then I'm going to turn off the lights. And then I'll do a shoot. And in about 60 seconds, we should see the Dumbbell Nebula, hopefully. Sometimes, you know, we have to do a couple of trials because sometimes the telescope doesn't point, you know, exactly where we want it to, but hopefully we'll see that.
Would you take another question?
Yes, go ahead.
Cassandra wants to know if a white dwarf star turns into a black hole.
No, white dwarfs cannot turn into a black hole. There is a condition, you know, on the mass of the star when it can become a white dwarf, a neutron star, or a black hole. This condition was actually discovered by Subramaniam Chandrasekhar, an astrophysicist at the University of Chicago. He found out that for a star to become a white dwarf, it has to have a mass of about 1.4 solar masses, the mass of the sun. And for a star to become a neutron star, its mass has to be about 3 times the mass of the sun. And for a star to become a black hole, it has to be a star of mass about more than 3.3 solar masses, or about 5 solar masses. So we know that our you know, sun is not going to become a black hole because its mass is just enough for it to become a white dwarf. The object that I showed you previously was a white dwarf in the center. So this object that you're looking at is the Dumbbell Nebula. Its Messier designation is M24. You might see some, you know, a shape in the form of a dumbbell here. I'll try to point it out. Now, depending on the orientation of your monitor, you know, I can probably increase the contrast, try to increase the contrast here a little bit. Let me go to the stretch here. There it is. You can see that here a little bit more clearly. This is in the constellation of Vulpecula, and it is at a distance of about 1,360 light years. Its size is about 1.44 light years. And again, remind you that 1 light year is about 6 trillion miles. Astronomers have calculated that the age of this object is about between 3,000 to 4,000 years. and its shape is proloid spheroid. And again, this is called a Dumbbell Nebula, also commonly known as the Apple Core, and it's another planetary nebula. The central star, which is right here in the center, is also a white dwarf of about 0.56 solar masses. All right, I'm gonna ask Larian to go to one of the planets. Larian, can you go to one of the planets? All right, so you should be, as soon as he is ready, you will see, and the image settles down, you will see Jupiter and its 4 moons.
I'm on Jupiter right now.
Okay. Okay, thanks. Stay there. All right, so Jupiter's 4 satellites are Callisto. Oh, no, we're not. Okay. We need to.
Did we disconnect?
Did we disconnect? Let me share the screen again. Right? Yeah.
Oh, there it is.
Right? Okay, great. Thank you. All right, so you should be seeing Jupiter. So did we not see Dumbbell? I can go back to it again. All right. Okay, so you see Jupiter and its 4 moons. Because this is a manually operated telescope, my student helper has to move it and keep it in the view. But you can see the 4 moons of Jupiter. These are Callisto, Ganymede, Io, and Europa. Jupiter is a gas giant. It's mostly hydrogen and helium. It's 3/4 hydrogen and 1/4 helium. It is named after the Roman god Jupiter. The satellites, you can actually, if you keep tracking of it, after a few days, you will see a different configuration of the satellites. And that tells us that, these satellites move around the planet itself. Galileo observed Jupiter with a small telescope, and he saw these satellites moving around Jupiter. And then that's when he realized that if Jupiter has its moons going around it, why doesn't Earth then? Why can't we not believe that Earth goes around the sun? Okay. So that was one of the observational evidence that Galileo provided to, propose that in our solar system, the sun is in the center of the solar system and not the Earth. All right, so I'm gonna go back to my previous object here. Let me make sure that you're seeing this Dumbbell Nebula. No. Okay, good. All right, so I'm just going to make sure that you saw the Dumbbell Nebula. It's again, there is a white dwarf in the center here. Okay. And again, I'm going to switch back to Jupiter for a few seconds here. Now, normally you can see the 2 brown bands on the planet itself. They're not visible with this small telescope and camera. The camera that we have it's a pretty nice camera, but it's not a very high resolution camera. So you don't see a lot of details on the planet surface there. All right, so now I'm going to go ahead and move to another object, a deep sky object, one of the galaxies. Is there any questions, Marian?
Not so far.
I'm sure you can hear the dome rotating. I'm go ahead and take a snapshot, and hopefully we will see a spiral galaxy. And this is the Messier object number 74 in the constellation of Pisces. All right, let me go to medium. I'm going to try one more shot and see if I can improve the resolution, the image. Move to another galaxy. All right, I'm waiting for the image to show up. I think we may be, let me zoom in. You can see, a little bit of faint arm, so I'm going to increase the exposure time a little bit more. In fact, I'm going to change the filters. Do 160 seconds, and you should see a better view in a minute or so. to focus as well. Larian, we're not ready for a planet yet, so I'm gonna tell you when we will go for Saturn.
Okay, thank you.
All right, so this is a spiral galaxy, M74. This is in the constellation of Pisces, and I do need to focus it. It's not very well focused. So I'm going to go ahead and, focus it a little bit. And then you'll be able to see a little bit sharper picture. So now with this telescope, when you have to focus it, what you do is change the focus, take another snapshot, and then, change another, take another, change the focus, change another snapshot. So I'm gonna try to do that here. So you see that it has improved a little bit. In fact, if you look at the screen, so when I have almost a perfect circle, that means the telescope is focused very well. So I'm taking another snapshot. I've changed the focus, and you can see that also by the shape of the bell curve over here. Okay, the sharper this bell curve is, the more correct the focus is. Okay, so I can go a little bit more, to improve the focus, but I do want to show you the galaxy again. So I'm going to take another long exposure. And you will see a little bit better view of M74 or the spiral galaxy. So it will come up here another 30 seconds or so. Any questions in the meantime? Okay. If you have questions, just put it on the chat on the YouTube. Now, this is a much better, view. It's a little bit more focused, but you can see the spiral arms. Our galaxy is very similar to this shape. It's also a spiral galaxy. And students often ask me, how do you know that our galaxy is spiral? Because we are inside on Earth, inside the galaxy. And the way I explain to my students is that what astronomers do is they count the number of stars in a small pie all around in 360 degrees in both directions. And then from the distribution of stars, they can map out the shape of the galaxy. So our galaxy is a flat disk type galaxy, and it has spiral arms. And you will also see some other galaxies which are edge-on rather than face-on. So this is a face-on galaxy. So you are looking at as if you are looking at it from the top of the galaxy. Okay. Here's the core of the galaxy. Many of these galaxies have active galactic nuclei, and there is active electromagnetic radiations coming out of it, and astronomers also capture these electromagnetic radiation to do different kinds of astrophysical studies. Many of these galaxies have been found to show supernovas. Supernovas are very massive stars that have exploded in a gigantic explosion, and they are often believed to be objects that produce the chemical elements that we find in our universe, all the hydrogen, helium, lithium, carbon, oxygen, nitrogen, and so on and so forth.
Good question.
Yes.
You wanted to know how spiral galaxies know. Four.
Four?
Yes.
Okay. Well, now astronomers believe that initially the cloud out of which the galaxies were formed were just spherical in shape. And so as there is a spin to that cloud, and so the spinning motion begins to flatten the cloud into a flat shape. All right. The faster the spin, the more flatter the galaxy gets. And so the flat shape that you see for spiral galaxy is believed to come from the centrifugal forces that is squishing the spherical ball of cloud and gas into a flat shape. Our solar system is believed to be also formed into a flat disk from the same principle, centrifugal force. Initially, the solar nebula was a spherical cloud, and as the sun was formed in the center, the whole cloud was spinning on an axis, and the centrifugal forces flattened the shape into a flat disk shape. So today we see all the planets mostly just going around the sun in one plane, elliptical orbital plane. Okay. So that's the explanation astronomers provide for the flat shape of the galaxies. I'm now going to take you to planet Saturn. And you will see Saturn with its ring. Now, what's interesting about these rings is that there are actually many gaps in the rings. And the scope is not high power to show you all the moons of Saturn. But what is interesting about these rings is that it so happens that this year, the rings are showing a little bit of face there. Another year, next year, if you see Saturn, the rings will be in a different orientation. You might see them to be just an edge on, okay? And sometimes you see the rings completely face on too. Now, again, this is a gas giant. Astronomers believe that there is a rocky core, mostly made up of nickel and iron, inside the planet there. Saturn has many moons. I don't even remember all the names of the moons there. But NASA has been sending a lot of space missions, satellite missions to study these planets in more detail. So I'm going to stay on the planet for a little while so everybody has a chance to look at it. So you can see the planet drift in the sky. That is because the telescope that we are using to capture Saturn is not computerized or does not have drives on it. So it doesn't move at the same rate as the planet is moving. So after a minute or so, it will be out of the view. And so my student has to bring it back into the center. And that's why you see a little jitter, occur in the image itself.
Jason has a question. He wants to know what objects can he see with only a pair of binoculars?
Oh, yes. Also, binoculars come in different powers, sizes, right? So depending on what binoculars you have, you should be able to see several of the major objects. Of course, you will not see a lot of the details. All the planets, you should be able to see Saturn, Jupiter, Mars. You may not be able to see Uranus very clearly, and Pluto. And of course, they are hard to find in the sky too, because they're not very bright like Saturn and Jupiter. However, if you're familiar with a software called Stellarium, it's a free software that you can download on your computer. It will show you where Uranus is and what time of the year it is visible. And you can take help of that software and then use your binoculars to hunt for Uranus. You should be able to see some nebulas as well, but again, you will not see a lot of details like you see here in the picture. If particularly if you look at M74, you will not see very clearly the arms of the galaxy like you can see here in my view. All right. So that depends, I mean, also on what telescope binoculars you have. Now, if you can mount your binoculars on a tripod, some binoculars offer that feature, then you will be able to, see the objects a little bit better, because then you're not shaking the binocular view with your hands, so it's more stable and the view will be a little bit better. So I would say, a few nebulas. The best thing to do is to look at the Messier catalog, and you can search for the Messier catalog easily on Google. All right. In fact, I will try to answer your question by showing you the Messier catalog. So on the screen, I've Googled the Messier catalogs of the month. What you can do, this is right now default to some month, but you can go for a 12-month index, and you can say, well, what are the objects that I can see in November? And these are all the Messier catalog numbers that you can see. If you click on the link, we saw this earlier with our telescope, the Ring Nebula Alpha Lyrae. This is the picture taken by the Hubble Space Telescope. Okay. Now remember, Hubble has a very great advantage of being in space, and plus it has color CCD. In fact, they can produce color pictures. We can also produce color pictures of our objects, but that is a little bit more work, because our CCD camera is a black and white CCD camera. We don't have the ability to produce direct color images. But I will show you one object that we have used to produce color pictures. Give me just a minute here to bring up the object. And this is going to be the Orion Nebula, which is not visible right now because it is below the horizon. It will come up later in the night. You can look it up there.
Bruce, I don't know how to say this. Brucina has another question, and they want to know how other planets, or how do we know what other planets and galaxies and stars are made of?
How other planets?
How do we know what they're made of?
Planets.
All of it.
All of it.
Yeah.
Okay. All right. Well, I'll try to, if I understand your question correctly, I'll try to answer it here. So let's look at our solar system. And if you understand how our solar system is formed, then we can, predict that this is probably how other planets are formed around other stars as well. So astronomers have found out from their studies that initially our solar system was just basically a spherical, cloud of gas and dust. All right. And there was a spinning motion to the cloud. And in the center of the cloud, the gas and dust began to collect itself into small globule and attract more mass, because when you have a pileup of matter in the center, its gravitational pull increases and it begins to attract more matter. And as the matter increases, the pressure inside the center of the object becomes, high, and temperatures also increase. At some point, the temperatures are so high that nuclear fusion of hydrogen can start. And we say that the star is born. And then as the star is born, there are lumps of material around the star, which are in form of rings that condense into planets. Some of them become rocky planets like our Earth and Mars. They're called the inner planets. And some of them are not, because the temperature in that region is not hot enough. They do not, collapse or condense into rocky material, but remain in gaseous form, like the giant planets Jupiter, Saturn, Uranus, Neptune. So that is how our solar system is formed. And we believe that other solar systems around other stars in our galaxy are formed in the same way. In fact, nowadays there is a great emphasis from NASA and world over by astronomers to search for different types of planets in other solar systems. And we have more than 3,000 confirmed extrasolar planets, which are in part of our galaxy. But hopefully one day, with James Webb telescope going into space next year, we hope that we will be able to actually search for planets in other galaxies as well. Right now, all we can do is look for planets in our own galaxy, but in future, we will have the technology to look for planets in other solar system as well. And there is an interesting, a calculation done by astronomers. This is called the Drake equation. If you have a chance, you can look it up on Google. What the Drake equation predicts is the number of possibilities of finding planets with intelligent life. All right. So think of this question in the following way. We know that there is one galaxy, which is our Milky Way, has one solar system, which is our solar system, has one planet, Earth, where intelligent life exists. All right. Now, astronomers have found out from their studies of the universe, there are potentially over 200 billion galaxies in the universe. All right. So just by looking at that number, if you're a very pessimistic view, we can say that if there is only one planet with intelligent life in every galaxy, there will be over 200 billion, planets with intelligent life. Okay, but that is just a very pessimistic view. If you're very optimistic and you say that a galaxy could have as many as 1 million planets with intelligent life, all right, there are 200 billion galaxies in the universe, over 200 billion. You can just multiply 10 million, 1 million by 200 billion, you know how many possibilities of finding intelligent planets with intelligent life on it. All right. So that's an interesting statistical estimate. again, these are all statistical calculations. That doesn't mean that there are 1 million planets exist in our galaxies with intelligent life. But there is another aspect of finding intelligent life, and that is that astronomers have found that it takes about 10,000 years for a life to become intelligent, and within 10,000 years, they are capable of destroying themselves. Okay. Now, many of these planets are so far away that by the time an alien is able to communicate with you, civilization on that planet has come and gone. Okay. Because radio signals take a lot more than 10,000 years to reach from some of the planets. They're so far away. So, I mean, it's quite possible that, by the time an alien civilization somewhere in our galaxy is intelligent enough to communicate with us, we may not be here. Or we are sending signals to planets where life has gone thousands of years ago. All right. Or maybe life is just beginning to start over there. So some interesting questions there. So what you're looking on the screen is the Orion Nebula. And this is the color picture. And this color picture was made with our CCD camera, which was black and white. And you will ask, how was the color produced? Well, that's how many of the research telescopes produce color pictures too. So what we do is we take pictures of the object in the blue color, in the visual, green color, and also in the red color. And we use a software like Photoshop and stack the pictures together, and this allows us to create a color picture. Okay, so what you see is the Orion Nebula that we had. One of our students was interested in astrophotography, and she took a picture of Orion Nebula in 3 different colors, and then used Photoshop to create a color picture of the Orion Nebula. So we can create color pictures, but remember, for astronomers, the science is not in the color. The science is in the light variation. All right, so I'm gonna go to another deep sky object, and probably we'll go to a globular cluster this time. Yeah.
Michael has a question and wants to know if we can see Saturn with the telescope.
With our telescope, the big telescope?
Yeah.
In principle, yes, but I will alert you, don't expect to find a dramatic view. All right, I'll try that a little bit later here in the next as a next object. In fact, let me see if I can bring up Saturn here. It will take me a few minutes because that is something that requires a little bit of work. I'll have to find the coordinates of Saturn.
Mars up.
Go ahead, Larian. Okay, so live video. That's not the one. All right, so what you see on the screen is Mars. As you can see, it's not going to show you much details. I'm going to try and bring up Saturn with my telescope, the big telescope. All right. Let's see. 1958, 51. Declination is negative 20, 59, 28. All right, so I'm going to try and point my telescope to Saturn. Let's see what we can find.
Do you want to take another question?
Yeah, go ahead.
Arthur wants to know what causes the spin of the galaxies and stars and planets.
Repeat that question again.
He wants to know what causes the spin of galaxies, stars, and planets.
Oh, what causes the spin?
Yes.
All right, so think of this as, a passing by star that can, create a disturbance, and that disturbance can set the object to in a spin motion. Okay, that's a very good question, actually. Lots of objects have initial spin as they're created in the universe. All right, so I am going to try and see if I can take a snapshot of Saturn. All right, I have to center it. Sixteen, 17, 11. All right, get ready. You're not going to see a very dramatic image. You will understand what I mean by when I say that, our telescope, the CCD camera, is not designed for solar system objects. Okay, so I'm going to improve on this image by cutting down the light. This was a 1 second exposure, but I'm going to cut down the light to about 90%. I'll still do 1 second exposure. All right. I can probably center it a little bit more, but maybe I can try that again. It'll get me a little bit better view. All right, so 1702, 1032.
Would you like another
Yeah.
option? Okay. Black holes have a surface.
Well, My answer to that question is no. Okay, it has a singularity in the center. Okay, black holes are just a point, but they do have a region which is called the event horizon. The event horizon is the boundary. When you cross that boundary, there is no force in the universe that can let you escape back from the gravitational pull of the singularity. Okay, so in that respect, you can call the event horizon as the boundary there. Let me see what happened to my object. There you go. All right. All right. You will be seeing a sequence of images. And let me change the resolution to planet here. And zoom in. Of course, I have to focus it. Let me see if I can focus this a little bit. Oh, going in the wrong direction. All right, a little bit more. All right, I can focus it a little bit more. Once I get a good focus, then I'll increase the exposure time to see if I can get a little bit more details. Right, let's increase the exposure time. Not really improving any focus that much. All right, so this is the view that we get from our big telescope. So you're looking at it from a big telescope. As you can see, I've increased the exposure time. It does increase a little bit the features in the ring, but you can see the planet itself is just a blob, you know. So and I can try different thresholds. Will probably not improve. Yeah. All right, so I'm overexposing. So I need to go less than 10 seconds here. Go something like 8 seconds. All right. So as I mentioned, it's a black and white picture because our CCD camera is black and white. However, I can take snapshots in blue, visual, and red, and then I can stack them to make a color picture. But that's a little bit, a process that you do after you have already done the observation. You cannot do it in real time with the setup that we have here for this telescope. Since this facility is designed to do scientific data collection for deep sky objects. All right, I'm going to go to another object. I'm going to go to a globular cluster, M17, 71. Any questions so far?
No, they're just commenting on how Saturn is so bright.
Yeah. I did change the focus. I'll have to refocus it for the deep sky object again. This is a globular cluster, so I'm going to go ahead and do for 20 seconds. I'm going to have to focus it again. So let's do 10 seconds first. All right, as you can see, let me zoom out, see what am I looking at. Not even pointing in the right direction. Okay. Out of focus.
We have another question.
Yeah, go ahead.
Daniel wants to know how you became, or how did you become interested in astronomy?
All right. Well, in my particular case, when I was in elementary school, during summer holidays, I like to read books. And one day my dad brought me a book on the solar system. And, in summer you have a lot of time and you don't have a lot of things to do since there is no school. So I read the whole book and I really found it very, very interesting and enjoying, And I told my dad, if he would buy me a telescope. So the next couple of years, later, he bought me a small telescope, and that's how my interest in astronomy started. I was just a young kid at that time, and we are talking about the early 1970s. During that time, also there was the sci-fi series Star Trek, which I loved it a lot, and that's how my interest in science and astronomy started. All right. Uh, I wasn't particularly a gifted child in terms of mathematics. I didn't care much about mathematics, but when I studied astronomy, I read books. I realized that if I want to be an astronomer, I'll have to improve my math skills and be very good at physics. So when I was in middle school, I would use my free time and brush up on math and practice math. I would do calculus problems, I would do physics problems, and that's how I developed interest in physics and math, and I improved my skills. And I did very well in school in physics and math. And then I realized that, this is something I can do in college, and then go to a college where there is an astronomy program. When I first went to a university for my undergraduate, there was nobody with astronomy. None of the professors were interested in astronomy. And so, it was kind of a little bit of a disappointment for me. So when I came to US for graduate studies, I decided to, find a school where I could do my PhD in astronomy. And so that's how I became an astronomer. And for that, I'm an observational astronomer. In astronomy, you have different routes and different choices that you can select. But I went to a school where they had a telescope, an observatory, much like the one we have here today at Tarleton. And I was kind of fortunate enough that I ended up using that observatory for many, many years. And, I learned a lot of skills in observational astronomy that way. So I give that credit to my dad. My dad never went to school. I think he dropped out after fourth grade. He had to take over his dad's, business. And, but he always encouraged me to read books and, go to school. And he himself was an avid reader of books. He traveled a lot to different places in the world. And that's how I became an astronomer, because my dad gave me all the freedom to do what I wanted to do. So I'm still not yet focused on the globular cluster. Here I'm going to go and try and do that. I also need to recenter it. A little bit better here. Let's see if I can bring it into the center here. 280, 312. All right, well, it looks like I'm going to have to reset. It'll take me a while. Go back to my Bright Star catalog. I'm not pointing correctly at the globular cluster, so I'm gonna, do some alignment again. On a bright star, and then, all right, that looks good. So okay, reset encoders, and I was gonna do M71. And then I also need to change back to all right. I'm gonna do a 50 seconds, 25 seconds exposure. Let's see what we find. All right, let's hope that it'll be in our field of view, and then I'll talk about the object. All right, a little bit better, but not what I was expecting to see. So I'm gonna try another object. It's not. Nice. I'm going to go to another globular cluster and 56. All right. Let's see. Still need to focus a little bit. All right. So I can talk. So these are called globular clusters. Okay. As the name says, they are more spherical in shape, but there are thousands and hundreds of thousands of stars in these clusters there. Okay. I can improve by taking a little bit longer exposure. So while it is doing that, I will go ahead and say something about globular clusters. So globular clusters are very, very old clusters. They are found in the halo of our galaxy. So our Milky Way is like a spiral galaxy. So think of it like, two cowboy hats put, upside down together. Okay, so you see the disk as an edge-on view. These globular clusters are all around the center of the galaxy, and there is a halo around the galaxy, and they're found in the halo. Now, astronomers have found that these globular clusters are very, very old clusters, as old as our galaxy is. Okay, and the stars in this galaxy are also very old. They are mostly hydrogen and helium. They don't have much metals. Okay, so these are called globular clusters. Now there are other type of clusters which are called open clusters, and open clusters have stars that are young stars. They are relatively young in age, and the metal content all right, Huh?
according to Jax.
Okay. We should do that. I'll do exposure and see what we see. Okay, so I'm trying to, look at a galaxy in a few minutes here. I'm going to increase the exposure time to get a little bit more.
Would you like to take a question?
Yes, go ahead.
Arthur would like to know that given the amount of stars close to each other in the cluster, why do the stars not run into each other due to gravity?
There is also because they're moving around, they have, also, uh, uh, centrifugal forces that keeps them from running into each other. So if they stop moving, then yes, gravity will pull them together and they will start colliding with each other. But because everything is in moving, motion, so centripetal forces and centrifugal forces keep them from colliding with each other. The same reason why moon doesn't fall into the Earth as it orbits the Earth, or why Earth doesn't fall into the sun. Okay, that's because as it goes around the sun, there is a outward force that keeps the object from falling in. Okay, I'm trying to, find us another object. It will take a few minutes. All right. We have seen this Ring Nebula. M57. So I'm going to try and find another object. Let's see. Helix Nebula. Oh, Andromeda. There was a request for Andromeda Galaxy, so I'm going to try Andromeda. All right. Okay, I'm going to take a few snapshots. It will take me a little bit of, trial and error here. But let's see if we have Andromeda. And there it is, Andromeda, but I'm going to increase the exposure time a little bit so I can get more of the Andromeda Galaxy. Let's do 30. And then I'm going to change.
We have another question.
All right.
And Cassandra would like to know if you think there is intelligent life out there.
Well, a very good question. I'll just give you a quote from Carl Sagan, the famous astronomer. He said that, if we are the only intelligent life in the universe, that is awful lot of waste of space. All right. So the universe is so big that it is kind of, hard to believe that there is no other intelligent life in the universe. So my own personal, view is that there are life in the universe, maybe not the life that we know as we know. All right. There may be other forms of life that we have no idea about. So unless we have the technology to visit other solar system and search for life in other planets, then that would be a different thing. But anyway, I'm going to go ahead and show you Andromeda Galaxy. Now, if you, that is how Andromeda Galaxy shows up on the monitor. Okay. In fact, if you change the contrast of the screen, you can see the arms. This is the Messier catalog number M31 in the constellation of Andromeda. That's why it is called Andromeda Galaxy. It's about 2.5 million light years from us. And its size is about 110,000 light years. So from all the way from here to here is 110,000 light years. Now, what you see is the active galactic nuclei, the core, but then there is the bright proportion of it. And then there is also very faint hazy spirals that you don't see, okay, in this image. So unless I process the image a little bit better, you may not see the whole shape of the galaxy there. And what we can do is we can try a little bit larger exposure to see if we will find any trace of the outer regions of the galaxy. So I'm going to do a 60-second exposure, and then we'll see what we find. Larian, are you able to catch Pleiades? So a new image will come up shortly in a few seconds. All right, so I've increased the exposure time to 60 seconds, and now you can see some more, details in the galaxy itself, so the dark areas there. I'm also going to show you some of the other pictures that we have taken with this telescope. While my student is trying to, capture another object. All right, so on your screen, what you see is M51. This is called the Whirlpool Galaxy. And you see two galaxies in there. I'll give you a little bit of information about this. This galaxy is about 23.16 light years. Now, this is not visible at this time of the year. This is an image that we took at another star party. I think this is in the spring. It usually comes up in the sky in spring. This is in the constellation of Canes Venatici. It's an active galactic nuclei also. The age is about 400 million years. And you can see that it has a companion galaxy near it. Okay, so astronomers believe that there is a interaction going on between the two galaxies. The big galaxy is quite large, and probably it is sucking up matter from the smaller galaxy. And so in several 100 million years, either this galaxy will be completely eaten up by the big one, or they will both collide and merge together. So galaxy collisions are pretty, common. Astronomers have found many examples of galaxy collisions, and there is an active research going on into understand what is the physics behind, galaxy collisions. Then I'm going to show you another object. Here. That we have taken with our telescope. All right. This is the Eagle Nebula. All right, this is the catalog number M16 and major catalog. It's an open cluster. You can see many, many stars here, but you can also see a patch of cloud and dust. And this shape, it looks like an eagle here. Okay, this is where astronomers believe new stars are born. Okay, this was taken from our observatory, uh, and you can see the cloud of dust and gas there. This object is about 7,000 light years from us, and has a size of about 70, 70 times 55 light years across. So it's a square, it's like a rectangular area. So about 70 to 55 light years, a rectangular shape. And it is believed to be about 6 million years old. All right, I'm gonna try and grab another object here. This is M81, Messier catalog number M81. This is a spiral galaxy in the constellation of Ursa Major. And the arms of the galaxy are very tightly wound together. Some galaxies show the arms very spread apart, and some galaxies show arms very tightly wound. As you can see, the traces of indication of one of the arms here and the arms here as well. Here's another galaxy. This is called the Black Eye Galaxy. This is also a spiral, and you can see this dark feature going across the galaxy. Okay. You see can't get the window in the view. Are there any questions at the moment?
Not at the moment.
Okay. All right. Larian, try and see if you can catch Alberio.
Again.
Alberio, the double star. All right, I'm going to try and point to a double star, Alberio, with my telescope. I just need to enter the coordinates, and then we'll point the telescope to it. So give me a minute here.
Got it.
Got it? Did you get it?
Yeah, I got the star.
Okay, let me check. Can you focus it so we can see both stars individually? All right, I'm going to take a snapshot.
I keep trying to focus, and this is all that's coming up. But I did find another star that you can see two stars separately. If you want
Okay,
me to go to that one. It was in
okay,
the
go to that one
Andromeda
then.
Constellation.
Okay, go to that one.
We have one question.
Yes.
And Arthur wants to know how common is it for spinning binary stars to exchange planets with other bodies?
Other bodies. Exchange planets. And now I don't quite understand what you mean by exchanging planets. But astronomers have found planets around binary stars. Okay. But they have, because these things happen over millions of years, there's no way to catch a scenario where you can see a planet being, captured by one star or another star. Okay. All right. So I'm going to try and show you Alberio. It's probably too bright right now, so I'm going to go ahead and reduce the exposure time and see if I can. Not just too bright. Let me try. Yeah, you can see the two stars, but I'll improve on the image by adding a filter and increasing. Well, let's try 1 second first. Too much.
This star is called MU Andromeda.
Okay.
And I don't know if you can see the two distinctive stars.
Yes, we can see them. So this is a double star. You can see the two stars. Can you center it? Can you center it, please? You can see the change in color of the two stars. There's one star is bluish and the other one is whitish. So I'm going to show you Alberio from my telescope. These two stars are, double stars. And because my CCD is black and white, otherwise, if I had a color CCD camera, once you would see one star blue and the other one red. So these are binary stars. This is one of the binary stars or double stars you can see with binoculars as well too. Okay, it's in the constellation of Cygnus. So these stars are about 434 light years. They are easily visible with small telescopes and binoculars. And, in fact, one of the stars is a binary, and both of these are double stars. There is a difference between a binary star and a double star. A double star is simply two stars that happen to be very close. They happen to be looking close to each other only because they are in our same line of sight. They're not actually binary stars. A binary star, on the other hand, they are gravitationally bound, and both stars orbit a common center of mass. So one of the stars in this optical double is a binary, the other one is not. But the two stars that you see are called optical doubles because we are looking at them at the same line of sight. One is slightly behind the other. Okay, so they look very like as if they are double stars, but they are actually very far apart. All right, we'll go to another object. Let's go to M33. All right, my telescope is still taking time to point to that object. I'm going to start taking a snapshot. All right, we are also coming towards the end of our star party in about 5 minutes or so. So this will be our last object. If you have any questions, anybody has questions, you can put it on the chat group. All right, we should see an image shortly. I know why that happened, because I forgot to remove the filter. So let's try that again. So while it's capturing image, you can keep looking at these stars. You can, very clearly see the difference in color. In fact, most of the stars that you see in the night sky have slight tint or color to them, and the color of the star tells us the temperature of the star. Okay, astronomers can find the temperature of the star, the surface temperature of the star, by looking at the color of the star or measuring the color content of the star. All right, so the galaxy that you're going to see is called Triangulum. Right, this is in the constellation of Triangulum. It is at a distance of 2.73 million light years. Its size is about 30,000 light years across. Okay, it's called Triangulum just because it is in the constellation of Triangulum, but you can also see a triangular shape as well too. This galaxy is the third largest in our local group of galaxies. So just like, in the universe, stars in our galaxy are, spread around in the central disk and the globular clusters in the halo. But then if you go outside on a galactic scale, you see a group of galaxies that are kind of close to each other. And then there is a vast amount of empty space until you see another group of galaxies. All right. And then as you go out further into space, you begin to see there is a super cluster of galaxies, a group of galaxies. All right. And then as you go further out into space, you begin to see that, there are super clusters of galaxies in the universe. So our universe is quite big in that respect. Our galaxy is about 70,000 light years across and 10,000 light years in thickness. Okay, so if you had a rocket ship that would travel with a speed of light, then you could go from one end of the galaxy to the other in 70,000 years. All right. All right. Now, if somebody has any questions, we have another couple of minutes, a minute or two. Probably we'll run out of time. But anyway, thank you very much for joining us in our star party. And we will do this again in spring. If you get a chance, please join us again later in spring.